Welcome back, everybody. We will continue with presentations on what actually comes out once you have gotten data. And Martino Romaniello will tell us all about different flavors of data.
Yeah, thank you. I will try to keep it brief. So the plan for the next hour and a half or so is that I'll give an introduction, 20 minutes or so, that's the idea. And then Jörg will take over and show some demos on what to do with the archive, how to get to your data and things. And then we have another one after that, and we'll close at 12:30 or so. Now, this is probably the only thing that you really need to know. So this is the URL of the ESO archive, and this is what you need to know to access all ESO data. Okay, I'll get to some details now, but this is the portal to reach all types of ESO data. Proprietary, if you're a PI, and then afterwards for archive use. Let's see if it actually changes slide. So it is really all you need to know, and it's all you need. I'll get from me because it's not changing slides. So went from the first to the second, and then it took me too literally. Oh, I need to click on the thing. So is this the thing? Ah, yes. This is the thing. Great. Thanks. Clicking on the thing always helps. So like I said, the ESO Science Archive, and the URL was above, and it's very easy to remember, of course, archive.org, is the collection point of all of the data that come from the La Silla Paranal Observatory. And as you know by now, La Silla Paranal means, well, La Silla, Paranal, and Apex, which is literally in neither of those sites, but it's still part of the observatory. So this is the sub-millimeter antenna on Chagrin Tor. I'll get to some details later, but by and large, the content of the archive is that all of the raw data end up there, science and calibrations, and also science-ready process data you can take out and work on immediately. The raw data become available in the archive for you to download if you need to keep a figure in mind 15 minutes after they were taken on the mountain. It's a bit less than that. It's more like 10, but by and large, 90% are available within 15 minutes. So if you have some need for quick access to the data, this is a timescale you need to have in mind. The science data is subject to typically to proprietary restrictions. So you write your proposal, you get your data, and the data belongs to you and to you alone for 1 year. After that, it's fair game for anybody and everybody to download the data and do their own science, because this is a facility observatory paid for by public money. So the data, which is the ultimate deliverable, goes back to the public domain after an advantage to the people who created the data in the first place. There are exceptions. There are things, for example, called public surveys, in which also the raw data is public immediately. Calibration data is public immediately as well, but they don't have typically a lot of use without science data that go with them. So, and process data inherit the same proprietary rights as the raw data. So if there is a process file and the raw data is protected, the same applies for the processed file. So much for the bureaucracy of it. Let's talk a little bit more about raw data. By raw, I mean the things as they come out of the telescopes, okay? And they essentially come in two flavors, since it's the topic of the presentation, is the flavors of data, science and calibrations. Science is the thing you're most directly interested in, but there's nothing you can do with science data without calibrations. Okay, so the two things at the end go together, because raw data have to be processed to extract the science signal, remove whatever instrumental effects the instrument and the telescope have imprinted on the data, remove whatever the Earth's atmosphere has imprinted on the data. The atmosphere is a great thing to allow us to live on the Earth, but it's not such a great thing when it comes to astronomy. It superimposes all sorts of nasty effects on the data, and you want to calibrate them out. And then finally, you want to calibrate your data in physical units. We're physicists, after all. We're not interested in how many electrons a certain event generated on the detector. We want to know how many ergs that corresponded to. And you need to associate the science data to the calibrations. And this guy has two things. One nasty one, which is that calibration cascades are rather complex. The good thing is that the archive does the association for you. Now I will dare to see if it works. To click here, yeah, it does. Except that the thing came up again. I go to more. No, I don't go to more. Don't let me go to more. So what I do is that, so this is, it's a bit small, but this is the homepage of the archive, so the URL I showed you earlier. And let's do a query for some raw data. And usually it fits better in the screen than this, but so let's take some science data from XShooter. So you select the instrument here, you select, make the thing go away. You select science, and I really wish this. You order the results so that they make some sense. So the data is first, and let's take some data that are public. So taken more than 1 year ago, let's say from January 1st last year to the end of January also last year. Remember, the proprietary period is 1 year, so they should be public. Okay, so what you get is a bunch of XShooter files. XShooter is one of the instruments on the VLT, of course. You select one and you download. Okay, you have to log in. This is Jörg's login. This is your user portal account. And now the interesting part, finally. So now you have a choice. You can only download what you've selected. This is one science file. But like I said earlier, there's not much you can do with that alone. So what you really want to do is select that plus the associated calibrations. You submit your request, and the thing starts thinking on your behalf and it's scavenging the archive to associate the best calibration to the science file. You have downloaded. Bang, it's done. So this is the file you have downloaded. And if you click this plus sign here, you have all of the other files that you need to make sense of the science file. And you will see another thing. All of those 4 files at the top, the one without indentation, are science files as well. So the system figured out that the one file you've selected belongs to a group, reconstructed the group, and downloaded and marked all of the calibrations that you need. Okay? This is just to show that to calibrate this one file, you need all of, it's probably 20 or 30 other files that you need to do that. Okay, but one click does it, and it's very important, of course, that the best calibrations are selected. Otherwise, the data they don't make any sense at all. This is where I leave this off now, because what you actually do with the data once you've downloaded will be covered this afternoon by Lodo and Wolfram and John. And so this was just to access the data. Now a word about process data. The beauty of process data that are available from the archive is that you don't need to go through all of that. You have the data in a form and in a shape and form that's directly useful for science. Okay? Still, this is very handy, but it comes with a caveat that I'll get back to at the very end. The one thing that is important to understand about the content of the archive is that the process data come in 2 flavors. One is, let me go directly to that. One is highly processed, but with a given science goal in mind. They're not suitable for any science case. They're tailored by the people who originally took them to their own specific science case. But then the advantage of that is that it goes to a very high level of processing, okay? All the way to sourceless and physical quantities of the celestial sources. The other characteristics that they have is that they are coherent data sets. Okay, for example, you have one that covers the whole Southern Hemisphere. These are just the names of the projects, that the acronyms of the project that generated them. Or the whole bulge and disk, inner disk of the Milky Way. Or a survey of the transient sky, supernovae, novae, whatever, it's there. In some cases, also coordinated observations across wavelengths. The important thing here is that they are coherent data sets, if that suits your needs. Other flavor is, in a lot of ways, complementary. Okay? This is then not processed for a science goal in mind, but with an instrument mode in mind. So all of the data for instrument modes are processed. Did it change? Yes. And are made available to readily enable your science. Okay? The important thing is that, as opposed to the case before, the processing stops when a judgment on the science is needed. Okay? Because depending on what your science goal is, you may have different ways of combining images, for example, whether you want to preserve flux or whether you want to preserve the shape of stuff, or what is it that you want to do at the end. This data stops us a step earlier than that, but cover the whole history of an instrument. One quick word about phase 3, because some of you may have to go through this, perhaps. So phase 3 is the process by which processed data make it back to the archive. Okay, the details are here if one is inclined to details. The important thing is that phase 3, as part of this phase 3 process, which of course is called phase 3 because it comes after phase 1 and phase 2, is that there is a quality check on the products, okay? To ensure that the ESO archive is not just a big bucket where bits are stored, but it's a big bucket where bits with a scientific meaning are stored and can be retrieved and used. Last thing, the cautionary tale I promised at the beginning. This is true also for data processing, but it's even more true if you access data products ready for science from any archive, ours or any other one. The fact that it's easy doesn't mean that it can be done blindly, okay? You have to triple check the data to make sure that they really mean what you think they mean. And we have to do, of course, the same on our side, to publish only data that we think that we know mean what they mean. This is just an example, and by the way, it was picked up by Andrea, who's there in the audience. This was from the Magellanic Cloud newsletter, which is a newsletter that announces results on the Magellanic Clouds, as the title suggests. This is UV spectra, so an ESO high-resolution spectrograph on some variable star in the Large Magellanic Cloud. Okay? These people, a very experienced team of people, went to the archive and retrieved from the archive a time series on this object. Okay, this is hardly something you can do without an archive because it spans a large amount of time, and observing time also, and also physical time that you need to cover this. Okay, so they did that and they found something interesting. They found an emission line here in the spectrum of this early epoch, which they identified with helium-2, because it's sort of in the spectral region of helium-2. And this thing does a bizarre thing. Here you see a blow-up of the time series. It fades with time. It's here, there, and it disappears a few months later. Okay? Bizarre thing, bizarre thing, is that this is the opposite of what the total brightness of the star does. The more the star is active, the less it emits in this putative helium-2 line. Great result, okay? If it only were true. This again was discovered by Andrea, and when she saw this, she said, wait a minute, this doesn't look right. And in fact, it was wrong, okay? This feature here is an artifact of data processing. It's not in the data. So there are two lessons, I think, to be learned here. One is for us, we should try to publish data that do make sense. Okay. The other one is that when you use the data, even if they are so handy, you just go to an archive and download a product you can immediately plot and publish, you need to go through the due diligence of making sure that the result is correct. And in this particular case, and this is no blame on anybody, but I mean, just as a matter of fact, just in the files, next to the column with a flux, which is what plotted here, there's another column in the table that contains this data that would have told anybody who looked into that this result was fake. Okay? So don't stop at looking just wavelength and flux or whatever you think is most interesting. All the other information that comes with the data is just as important to make sure that, first of all, the data is useful, and then second, that you really understand all the caveats that go through the data, that go together with the data. Thanks. Okay? You will hear more examples along these lines. When you reduce the data, you can make sure when you reduce the data that this is the case. But again, it's so tempting when you have data already reduced not to go through this, that it's so important that you actually do that. And this is, I think, all I wanted to say. Thank you.
Questions for Martino?
So I was wondering if I should download my Spectre with wall calibrations or with process calibrations. So in which case would you recommend which kind of calibrations?
I think that it really depends what you want to do. And another way of saying it is that it depends how much you trust us. To which, of course, this applies. I think that the first thing would be try, if there are corresponding process data, go first with the process data. See what it looks like. Have a feeling for what they contain. And then go to the raw data. Personally, but this is my personal take on this, if you really need to go to the raw data, which is a very valid case, I would start from scratch. Okay? Raw science, raw calibrations, we have full control. The system that you will be seeing later today allows you essentially with one click to process the whole thing from raw calibrations. And that's also a way to make up your own mind on the data reduction. And then take it from there.
So with the pipeline, it's not much more time consuming to start from scratch, basically.
Well, it depends on the pipeline, but at the end of the day, I mean, time consuming is one aspect, but being accurate and getting to results that do make sense takes its time. So, but again, this would, starting from the products, will cut all the time in between and gives you a feeling. And then you take it from there.
Okay, thanks.
We have more questions for Martino. Anybody online that would like to ask a question? If not, let's thank Martino again.
Thank you.